What has zero moving parts, yet can blast an aerial vehicle to velocities beyond Mach 5? The answer is the recently flight-tested atmospheric test of Launched Air Breathing System, ATLAS, powered by a new solid-fueled ramjet built by GE Aerospace. Hypersonic missiles capable of flying well in excess of 5 times the speed of sound promise to revolutionize warfare and aviation in general in a manner not seen since the sound barrier was broken in 1947. Not only could it turn flights from London to Sydney into an afternoon jaunt instead of a 22-plus-hour ordeal, it could also make current air defenses obsolete as vehicles blast by before defenders would even detect them. The tricky bit is how to get the vehicle into the hypersonic range where it can cruise under its own power or fly as a Mach 5 plus glider. For the ATLAS program, GE Aerospace has come up with the latest in solid-fuel ramjet, SFRJ, technology that seems to operate almost by magic. Ramjets look more like a conjuring trick than technology until you figure out how they work. Look inside a ramjet engine, and all you'll see is an empty tube. Switch it on when it's on the ground and all you'll get is the same hollow tube with jet fuel squirting into it, achieving nothing. That's because a ramjet operates on a different principle from a conventional jet engine. The kind of engines that power an airliner uses a series of fans and turbine impellers to draw in air and compress it on the way to the combustion chamber, where it mixes with fuel and burns to generate thrust. A ramjet does essentially the same thing, only it doesn't use any moving parts. Instead, as it moves through the air, its own speed causes the incoming air at the engine inlet to compress itself and heat up by sheer inertia. This works so well that one of the key engineering problems of such engines is to design the air inlet to slow down the incoming air to subsonic speed before it heats so much that it melts the engine. The advantage of a ramjet is that it is a very simple, lightweight design that is ideal for supersonic flight and beyond. However, I wasn't being completely honest when I said that the ramjet has no moving parts. In fact, there are quite a few if you count the system to feed and regulate the liquid fuel going into the combustion chamber. Funded by the U.S. Department of War, GE Aerospace's ATLAS program takes simplicity to the next level by eliminating the liquid fuel by lining the interior of the engine with a solid hydrocarbon fuel that looks a bit like rubber. This isn't like a solid rocket fuel that carries its own oxygen along in the form of a powdered oxidizer mixed in with the fuel. It's just the fuel, with the air coming and providing the oxygen for combustion. As the fuel burns, it ablates, leaving a fresh layer of fuel to feed the flight. By not carrying oxygen, the engine is not only lighter, but it's more efficient. Where a solid fuel rocket has a specific impulse, a measure of rocket efficiency of about 240 seconds, the SFJR can manage 1,000 seconds. In addition, replacing all those mechanical parts makes the engine cheaper, an important point with what is essentially a disposable power plant. For testing, the engine installed in the ATLAS flight test vehicle was bolted to an F-104 starfighter that had been converted into a test platform that can manage speeds of up to Mach 2. According to GE Aerospace, the flights were necessary because wind tunnels couldn't provide the complex factors found in the real world, including vibrations and temperature stresses. For the tests, the ramjet wasn't lit, since the goal was to study aerodynamics. Besides, setting it off while bolted to a fighter jet would have been messy, to say the least. Actual ignition will have to wait for later free flight tests. This marks a pivotal moment for GE Aerospace as we showcase our solid-fuel ramjet technology in flight for the first time, said Mark Reddick, Vice President and General Manager of Edison Works Business Technology Development at GE Aerospace. Captive carry testing of reusable flight test hardware allows for more frequent testing in realistic atmospheric conditions to better understand system behavior.